Hey guys, welcome back to another video. So in this video, we're gonna have like a small Q&A session. I'm just going over a few problems people had from a few units back, or even the unit we're on currently. So if you have any questions, feel free to like comment down below if you want it covered. So the first question I got is how to tell whether a molecule is polar or non-polar. Obviously, if we had this chart, it would be way easier, but I think with a few tips, you won't really need it, and it'll be really quick and easy. So the first thing, check to see how many lone pairs there are around a central atom. For instance, if there are 1 or 4 lone pairs, you can easily tell if it's non-polar or polar. So if there's only 1 lone pair, you know for sure it's polar, because you can see from this column right here, these are all polar molecules. So this is polar, but if you see 4 lone pairs, it's only this one. It's non-polar. So 1 and 4, it's really easy to tell. The hard part is if there are 2 or 3. So 2 lone pairs mostly are polar. The only really big sort of exception to that is the square planar. So you really, for 2 and 3 lone pairs, you have to check steric number. So steric number is nothing but the number of lone pairs plus bonds, or bonds. So for instance, for 2, knowing the steric number will tell you whether it's polar or non-polar. For 3, for instance, is 50-50. If it has a steric number of 5, then it's non-polar, but if it has a steric number of 6, then it's polar. So it's all up, for 2 and 3, it's all up to looking at the steric number and sort of figuring it out that way. The next question I got is a really good question in my opinion. Basically, the trend for like acidity in hydrogen halides is like hydrogen chloride, like HCl. HCl is strong, HI is strong, HBr is strong. Why isn't HF strong, right? These 3 there's such a huge electronegativity difference, they're strong. This has the most electronegativity difference, yet it's not strong. And why is that? So this is a really interesting question, because the thing about fluorine is, even though electronegativity difference is huge, probably something even bigger than that is size. So fluorine is the smallest of all the halogens. So the thing about small atoms, especially fluorine, it has a very large charge density. So there's a large amount of charge per size. So it's very small, a lot of charge in a very small space. And the thing with that is, because it's so small, it has such a huge or such a big charge density, the orbital overlap, because it's so small, will be a lot larger, right? If you have H and F, this is significant, whereas something bigger will be very, very small, and so it'll be easier to sort of break, which makes it stronger. This makes it weaker. So size is very important. Another thing also, if you learn like in organic chemistry, you have all these really complicated atoms. A good way to know whether something is strong is if the conjugate base is stable. So for these, Cl minus, I minus, Br minus are more stable than F minus, right? These are conjugate bases. So these are more stable than fluorine because it has a lower charge density, right? Because charge is balanced throughout the entire large volume, it's a lot more stable. Whereas something here is so small, so much charge, it's not as stable. And because the conjugate base isn't as stable, it's so unstable, it's going to be a weaker acid. The last question I have for you here is another pretty interesting question too. It's the question says, why do ionic compounds generally dissolve anyways? So this person also specified like they know it's thermodynamically favorable, but is there like another reason? I guess the answer here is it is thermodynamically favorable, and that's where most of the answer is basically. But if you delve down a little deeper, you'll find out it's something else too. So I'm going to first talk about it thermodynamically and then see if I can connect it to something else. So first, for something like the solvation process is spontaneous, right? So delta G has to be negative. So delta G equals delta H minus T delta S. Generally, this is really small. So this is usually very enthalpy driven, right? So this delta H needs to be negative for this to be negative, usually. So if you look at delta H, it's literally delta H of, for the solvation, it's delta H of the solute delta H of solvent minus delta H solvent, right? So for this entire sort of, which is delta H up here, for this to be negative, the solute-solvent interactions have to be greater than this. So that and the solute and solvent have to be small. So this has to be small, this has to be big. Now usually this term is usually around the same, right? Because how water behaves with certain solids is usually pretty similar. The big determination, honestly, is how small these can be. So what this means is, like, what makes NaCl more soluble than like AgCl, right? And the main difference really is electronegativity. Because the huge difference in electronegativity for sodium chloride, it takes less energy to break this these two solutes, right? So you have a low delta H solute, and so this term sort of predominates. So electronegativity difference is a very big indicator of polarity, right? So the more polar the solute, the more polar the solute is, the more likely it's going to be soluble thermodynamically. All right, that's going to be it. Like I said before, don't be afraid to sort of put down any comments for questions. I'll be probably doing this a little more frequently.